So, we have seen yesterday this input data sheet, and it's very easy and friendly to use. Yeah? Then we have seen the analysis of scrap, and as I told you, this is the result of my, let's say, previous experience, but it doesn't, let's say that you don't have to change this scrap analysis depending on the information you get going on the scrapyard of the customer and having a feeling about the scrap quality. Okay? If you need special scrap training, we can organize scrap training. Eh?
Okay.
Huh? For example, when I started in the 90s, the scrap density of the HMS1 used to be 0.7. Nowadays, it's more than 0.6 or even 0.55. The density has decreased quite a lot.
Yeah, that's right.
Yeah,
because in these days, 0.3.
Yeah. Eh?
In these days, 0.3 is the commonized.
0.3?
Yeah.
Oh.
It's too low.
No, this is too low.
It's real.
This is definitely too low.
No, it's real. In Dong Steel also 0.3 or 0.36, and the South Asia is obviously 0.3. They use the light scrap only. They do not have the heavy scraps. And also in Japan, they did not get the H1, H2 class of the scrap. They use the light scrap only. In case of the Japan, they already dismantled the blast furnace, and you can watch the Osaka ground instead of the blast furnace, and they cannot get HR class. And they get only the turnings and some thin plate from the refrigerators and the cans
and the bicycles and stuff like that.
It's done. So in the world and in South Asia and other South Americas, and they will use only the light scrap.
다 그래요? 그러면 이거 압착하는 게 있잖아.
압착하는 거 있지. 프레스는 있지.
그거 써도 그렇게 나와.
프레스는 많이 못 써.
너무 낫다.
그치, 다 했어. 프레스를 쓰면 이게 또 많이 또 잘 안 먹거든. And also press the scrap.
Bundles.
No bundles, press the. It's a trash can and the car.
스케줄링
Car to press the scrap.
It's not bundled.
Not bundle. Bundle means it's the wires and the tight.
No.
The scrap. We said press the scrap.
Yeah.
Make a cubic.
Yeah, sure. This is bundle.
You bundle?
Yeah.
Okay.
Because it's the result of a press. Yeah. You put the scrap in a machine, and the machine closed, and then you have a piston, a cylinder to press it.
One car.
Yeah.
One bundle.
Yes, bundle.
Okay.
That's
Same
right.
meaning.
You have different bundles. You have the bundle number 2, which is, let's say, very mixed, and you see the iron content is rather low. Oh, it's too high here.
Too high.
But this one is very high because this is the automotive industry. This is directly from automotive industry.
That is also include so many carbon and plastic.
No, I mean yes, the coating.
Coating.
Yeah, some coating. Yeah. So you see the carbon. No, carbon is very low. Yeah, because this is the deep drawing steel.
Yeah, that's right.
Deep drawing steel.
Right.
Usually it's good steel, but we don't find so many. Because there is agreements between the automotive industry and the steel producer. so that these bundles, this revert scrap is coming directly back to the steel supplier, and they are using as a cooling scrap in the converter. So usually this kind of scrap is not going on the market.
Yeah.
Then we have liquid iron as well, and the temperature is not mentioned here in the liquid iron. It's supposed to be at 1360, 1350. Yeah. Because in fact there is a direct function between the temperature and the silicon. The temperature remains at let's say constant level as long as there is silicon available, and then the temperature drops.
Silicon?
Yeah. If you start with 1.5 silicon, then the temperature remains more or less constant, and the silicon is going down.
And temperature down.
Yeah. Below 0.7, then the temperature is going down.
보통 그렇게 됩니다.
네.
This is something I've learned from the specialist of hot metal.
금속 아래.
And for example, I've seen a huge difference in the furnace result, furnace performance, between Chagrin, for example, where the hot metal is tapped at a low temperature and has to wait for a long time because there are 15 hot blast furnaces or something like that. So the logistic is rather complicated, and there is a long distance to travel, about 3 kilometers to the steel plant. Compared to dragon steel, where the hot metal is coming from 200 meters and coming very fast. So for Chagrin, the energy ratio is about 3.5 kilowatt hour per percent hot metal, and in the dragon steel is going high to 5 kilowatt hour per percent of hot metal. In Severstal in Russia, it was in the middle, yeah, because the logistic is rather complicated as well.
지금 앞에 사강은 한 메탈 퍼센트당 3kW씩 절감을 했다는 얘기고, 드래곤은 5kW씩 이 정도 절감했다, 그런 얘기로 지금 얘기한 거죠? 이렇게.
Then we have seen that also DRI is provided here with a small calculation table here to calculate the amount of oxygen in the DRI. This oxygen is very important because it costs a lot of energy. In case you are using a huge amount of DRI in DRI or HBI in the furnace, you are obliged to reduce this iron. Yeah? So, in the lime and dolomite analysis, you see that there is water and CO2. This is the parts of the lime, and it's also to be considered in the thermal balance because the unburnt lime is requiring energy. Yeah?
Unburnt lime.
Unburnt, yeah. So usually we are asking the customer what is his lime calcination rate, and it should be in a range of 98%.
98%.
We had the case of I had the case of customer using, let's say, limestone almost, because the calcination rate was about 40%. And the energy difference is quite huge. Yeah? It's going to be 20 kilowatt hours per ton in this case.
그 한번
뭐 그런 거 수치되는 거는 뭐 심플한 건데 뭐 저 보통 CaCO3, MgCO3거든요. 그러니까 이제 소선한데 에너지가 필요한데 그거보다 뭐 연락각 데이터나 시스템 에너지가 필요해서 지금
근데 저희 얘기를 쭉 다 해주니까 우리 지금 일단 어떤 기본 야금 쪽에 접근할 준비도 그렇게 많이 안 돼 있거든요. 지금 스타트 하고 있는 과정이라서 일단 이제 들으면서 어느 쪽을 접근해야 되는지 전부 다 또 해야 될 필요가 있을 것 같고 대신 박사님과 같이 도와주면 좀 더 별도는 다시
Humidity is also important, especially in the countries where the humidity is rather high, in Asia, for example. Concerning coal, the ash and the sulfur are important. Ash content. For the injection coal, for a new project, you have to specify the volatile content of the injection coal below 1% or below 1.5%.
What is it below? Should be below.
The volatile, it is not specified here because there is no importance in the energy balance, but this is for the foaming slag.
탄화 물질이 0.5%가 있습니다.
Yeah, this is for the foaming slag. This is very important.
타는 물질?
그 성분, 카본 성분에 보면 저기 보면 H2O, CaO, MgO 등도 있고 또 발라타일이라고.
Volatile is not specified
여기는
here.
안 되는데 휘발성으로 타면 날아가는 성분이 있고.
Volatile is the quantity of CH4, more or less.
그게
Yeah?
1.5% 이하로 돼야 됩니다.
We can summarize at CH4, but these are, let's say, some oil, even some oil, not only gas, but some oil impregnating the coal. Yeah? Because coal is the fossil wood, yeah? Fossilized wood.
Wood.
Yeah? So in fact, you have also, I mean, it has, let's say, got a lot of pressure, and you have some porosity in the coal. So inside this porosity, you have gases and oils. Yeah? So these are the volatiles. So you have coal with low volatile and high volatiles.
네, 그 카본, 그러니까 콜을 기본적으로 구성되어 있는 게 픽스드 카본이고요. 그다음에 이제 애쉬, 저기 애쉬나 이제 CaO, MgO, 됐어요. 그다음에 이제 VM, 볼라타일 멘타. VM은 일반적으로 이제
VM이라고
예, 볼라타일 멘타. VM.
This is the ash, yeah? This is the ash. Volatile is different. You know why the volatile has to be low.
VM이 중요한 게 CH4가 크래킹이 일어나야지만 그 탈이 발생이 안 된다. 쿨링할 때. CH4가 크래킹이 일어나려면 1050도 이상 정도가 이제 반드시 온도가 돼줘야지만 크래킹이 이제 완전히 C하고 H 형태로 분해가 돼서 구공정에서 이제 쿨링할 때 그 타르가 생기지 않아서 이제 타르가 생기면 당연히 이제 그 어떤 막힌 문제라든가 이런 게 발생할 수 있거든요. 그런 것들이 중요한 문제고.
I don't know what this gentleman need explain.
Yes, I introduced our colleague, Mr. Park. He is a metallurgist.
Yeah.
He is you remember?
Okay.
He worked for POSCO ENC a long time ago, and he come back again. Yesterday, he came here. Please.
Nice to meet you.
명함이 안 났죠?
네,
I met you shortly yesterday afternoon. Yeah. So, despite of what he explained to you, I heard cracking. So maybe it's in the topic, but let me do my job. We are the metallurgists, so we cannot understand fully, but Mr. Park, no problem.
No explain more.
I will take this one. computer is getting low now. Huh? Okay. So this is short explanation for the foaming slide. When you inject carbon in the slide, you see this is particles of carbon here, and they meet the FeO of the slide, and then it creates a small CO bubble around. Yeah? And of course then the lifetime of the bubble in the slide made the thickness of the foam. Okay? If you have fine coal, you create more bubbles, so it's easier to foam. If you have bigger grain size, you have less bubbles, so it's the foaminess is not so easy. Yeah? But if you have high volatile, the carbon is coming in the hot atmosphere in the furnace, and you start cracking, as he said, the volatiles of the carbon. And the carbon cannot penetrate in the slab because the gas generation avoid that the carbon is penetrating. Or even creates, even if the carbon is penetrating into the slag, the carbon grain is surrounded by a bubble of these volatiles. And the carbon has no more, let's say, contact with the FeO. So it doesn't create additional CO. Yeah? So you may do this experiment sometime, and you will see that the foam is not created by the high volatile carbon. Huh? Okay. Then we were stopped at the natural balance. I will try to remove this stuff here. I don't know. Oh, we are lucky today. This button is not changed. Yeah? Okay, so we have seen that this column represents this one here. Yeah? Then you have the liquid iron and the DRI to, let's say, because this is the table, this part of the table I give to the customer. Without this small stuff. So whenever there is liquid iron, the customer likes to see that I have calculated with the liquid iron. Yeah? So we have seen yesterday that the steel analysis is coming from the input data here, carbon at tapping. Then mangan is calculated with this equilibrium, phosphorus and sulfur as well. Yeah? The Fe is the 100 minus the rest of the elements, and the oxygen is given by the, let's say, the thermodynamic equilibrium when the carbon has reached the 0.09, and depending on the temperature as well. Yeah? Because this is input data D22. D22 is the tapping temperature. Huh? So even it would be easy to change it directly and to put tapping temperature, because I use names usually, but I didn't change everywhere, so it's page 22, it should be as well the tap carbon. Yeah. Uh-huh. There should be a name. Okay. The dust is a standard analysis. Yeah. And here the amount of dust, we have seen that it's for standard conventional EAF, modern UHP is in the range of 18 to 22. Yeah? Of course, in local conditions, if you have dirty scrap, you may have more dust than this amount. Yeah? Okay, let's go back to the slide. So the first step in the calculation for slide is the SiO2. The SiO2 is calculated by the amount of oxide which is charged into from the scrap, plus the silicon which will be oxidized. So here you have N16. This is this SiO2, N6 is this silicon times 2.139. This is to convert Si into SiO2. Yeah? Minus the silica which is consumed by the dust. Okay. Then Al2O3 is the same, except that we don't suppose that we have metallic aluminum in the scrap. Okay. For sure there is some aluminum metallic in the scrap, but in very low proportion.
Very low.
So it's not worth to consider it.
What did I consider?
No. In Japan, you have to know that Japan is the first, let's say, consumer of aluminum scrap, because the electricity in Japan is very, very expensive. So they buy worldwide a lot of aluminum scrap, cans or whatever, engine blocks. And this is going to the, let's say, secondary aluminum metallurgy. So they just melt the aluminum scrap and in induction furnaces. And of course, on top of the aluminum, you have ashes. Yeah? It's not slag, it's ash, because it's not liquid. So the ash is removed, but still have between 30 and 40% of aluminum, metallic aluminum. This is crushed and sold to the steel industry, because this ash is polluted with iron. Iron is a poison for aluminum. And steel plants are using a lot of this kind of aluminum powder. It's upon a time it was on the market a product named Alumix. Alumix is just to say mix of aluminum. So they are using it to inject sometimes directly in the furnace to make aluminothermy, to increase the temperature of the bath. Sometimes in a ladle to make desulfurization, really to kill the oxygen of the steel, and even to let's say increase the slag with Al2O3. We will see when we will look on the LF model that alumina is very helpful for the ladle furnace. Yeah? So that's why I consider Al2O3, I mean aluminum, only as oxide for the scrap. Yeah. So then CaO is calculated based on the target basicity. Yeah? So I just consider the silicon times the basicity, and this is the amount of CaO I will have in the slag. Alright? Then we come to the MNO. MNO is, as you see, the quantity times the weight of slag. So, in fact, I have to jump to the slag weight. We are able to calculate the SiO2, Al2O3 and CaO by this way. Yeah? But to calculate the total amount of slag, we have to make a trick, because the other weights we don't know, because it depends on an equilibrium. So I am able to calculate the P2O5 content of the slag, thanks to the equilibrium between the slag and the steel. Okay, by this formula we have seen yesterday. I am able to calculate the sulfur content of the slag as well. I am able to calculate the MNO content of the slag by the equilibrium as well. MgO is an input. This is the target MgO content I want in the slag. Because for MgO I have two solutions. Either I don't put dolomite in the slag and I just rely on the refractory to saturate the slag with MgO, which is not very good practice, because then I have to repair the furnace nearly every 2 heats, and refractory material for repair costs money, repair time costs money and energy. So this is first practice. You still have steel plant doing this. The other possibility is to charge dolomite or MgO balls or whatever product containing high magnesite. It can be used refractory, crushed, used refractory or whatsoever. Right? So that's why here I put a target MgO content, and you have to discuss with the customer to know what kind of practice he would prefer. Yeah? Typically, if you don't put dolomite in the slag, the average, let's say, MgO content of the slag is in a range of 6%, coming from refractory material and from the GAN of the scrap and the dirt of the scrap. Scrap is all the time dirty, because scrap dealer likes to supply the trucks with their scrap, but also with the ground of their yard, to put some more weight in the trucks. Yeah? So that's why this is a target. So I know the MgO content. Iron content is also a given figure, because it depends on the good practice of the operator. We could put, let's say, a thermodynamic equilibrium for the iron content depending on the carbon content. But what about the foaming slag? I was able to reach 100 ppm of carbon. Here, 100 ppm of carbon with iron content of 15% in the slag. Yeah? Which is far away from the, let's say, equilibrium slag, steel and slag. Because on the slag you have 3 influences. You have the bath carbon content and oxidization level. You have the furnace atmosphere containing oxygen, and you have the carbon injection. So you have two oxidizing factors, the bath and the atmosphere. I mean the bath, that means the oxygen injection in the bath. Yeah? And the furnace atmosphere. And one reduction factor, which is the carbon injection. Everybody's following? Huh?
좀 어렵고요.
우선 먼저 슬랙은 기본적으로 아까 임지용 이야기 나오신 거 있는데 잘 아시겠지만 기본적으로 슬랙 케미스트리라는 슬랙은 특성상 세츄레이션 그 온도에서 세츄레이션이 일어나기 때문에 내화제가 예를 들어서 선택을 잘못하게 되면 그리고 슬랙이 잘못되면 침식이 됩니다. 그래서 이제 MGO 같은 경우는 이제 아까 유괴에서 짓고 그렇게 이제
오케이.
일반적으로 저희가 쓰는 그 사용처에 따라서 다를 수 있어요. 그런 상태에서 MGO를 잘 맞춰야 됩니다. 그다음에 이제 FP는 스펙 중에 FP는 FPO 형태를 그리고 이제 아까 슬랙 포밍에 상당히 의존하는 뭐 그런 카본 슬랙 포밍이 잘 일어나면 FP를 줄일 수 있다는 그런 이야기를 하셨거든요. 그거는 제가 요거는 조금 확인을 한번 해보겠습니다. 기억이 잘 안 나는데 감이 좀 오래돼가지고.
이제 우리 녹화하고 있으니까 비디오 해서 다시 한번 더 확인해.
이거 하나 좀 갖다 주세요. 이대로 가지러 간 거 아니야?
그런 것 같아요.
So,
밑에 히웰 브랜드 초코.
now,
I cannot see very well.
you don't see.
You can see.
Because I can take the picture of my manual, but
It's not together.
I'd like to make.
그거 들어. 잘 나온 거 줘라.
Better. Okay. Here you have the bath. Yeah? This is the steam. On top you have the slag. And here you have oxygen injection. We suppose supersonic oxygen injection. Yeah? That creates a nice cavity. The consumable pipes. It is also possible to inject oxygen with consumable pipes. But we will see that it's not a very good tool anyway for the bath work. To clean the door, okay. So in fact, what happens at the impact of the oxygen stream? You create here around a small layer of iron oxide, pure iron oxide. This is easy to understand. You go to Africa, you are, let's say, an oxygen molecule. You go to Africa, you just see black people in majority. You go to Europe, you just see, except in the big cities now, you just see white people. So imagine the oxygen molecule arriving in Paris, just see steel molecules, steel atoms. So he's getting married with the white people, not with the black people. Okay? So, and then due to the bath movement, this iron oxide is migrating into the steel. And then you have a reaction, FeO, Fe plus oxygen. This oxygen is going to get dissolved in the steel. And the oxygen solubility is a pure, let's say, proportional to the bath temperature and also influenced by the sulfur, because the sulfur solution, the solubility in the steel is occupying more or less the same location than the oxygen. And this dissolved oxygen is going to realize the decarburization later. and then the FeO is meeting sometimes carbon which is dissolved in the steel. Yeah? And you start decarburization and you create CO, small bubbles of CO. Yeah? And at the end you have a bubble of CO and a remaining FeO. Okay? So this is what is happening at the impact of the oxygen stream. If you have high mangan, of course, you create FeO plus MnO. Yeah? If you have high silicon, you create as well silica. Alright? So you have a primary slag here coming to the top. At the end here, you have a mixture of FeO plus MnO plus SiO2. Okay? So if you don't do anything, your slag is getting richer and richer in FeO. And I've seen steel plants having at the end up to 50% FeO in the slag. And they don't care so much. They don't take slag analysis. But we are intelligent now since 30 years, and we know the foaming slag practice, because at the origin it was the Japanese who had invented the oxygen injection in the furnace, because the current was very high. So the electrical energy was very high, and they had the idea to inject oxygen to fasten the melting practice. But they have seen that the yield is going down. So they say, okay, if the oxygen is oxidizing the Fe, the cheapest way to reduce the Fe, because scrap is costing money, is to inject carbon. So they start injecting carbon, and they have seen that the slag is foaming. Carbon injection. Yeah. And if the slag is foaming, then we can increase the voltage. So we can increase the power. And then, and. You see? This is, let's say, the origin of the, let's say, modern electric steel making. Then Fuchs arrived with the water-cooled panels, and then now you know that one furnace is able to produce 1 million ton, even more. At the origin, a conventional mini mill was able to produce at least 200,000 tons a year, yeah, in the 70s. Okay, we inject carbon, so we have carbon particles. Yeah. If you have high volatiles, then you send already a carbon particle with a bubble around of methane or oil, etc. So this has no way to penetrate the slag. Even if you have even a high impact, you have a carbon particle surrounded by a bubble. How can it react? Not possible. But if you are able to avoid these volatiles, then you have a carbon particle moving into the slag and meeting the FeO, because the FeO is dissolved in the slag, so it's liquid, it's easy to react, and you create small bubbles, which are migrating to the surface of the slag. And the amount of bubbles and the viscosity of the slag and the interface, the condition at the interface between the slag and the bubble create the lifetime of the bubble. The lifetime of the bubble is the time where the bubble exists in the slag. If you have a small lifetime, you have low foaming slag. If you have a high lifetime, you keep a lot of bubbles in the slag for a long time, so you have high foam. Okay? Easy to understand, yeah? This is like the beer. Yeah. So this is for the forming slide. Now what happens to the dissolved oxygen? You have seen already boiling water. You take a pan, you put water on the gas, and the water is start to boil. And you look into the pan, what do you see? Decay.
Yes.
What do you see when you observe the water boiling?
Bubbles are generated from surface of pan.
Exactly. And it's exactly the same for the decarburization. You have the refractory lining, and you have here sites on the bottom of the refractory where you generate small bubbles. Originally it's oxygen, and it reacts with carbon, and you have at least CO bubbles. Yeah? This is originated on the bottom or in the impurities in the steel, because you may have some, let's say, particles of refractory getting up, some, let's say, inclusion of oxides in the steel, yeah, as A2O3 or some very small particles, generating these sites where you can still initiate the decarburization. The oxygen is not necessarily at the equilibrium. Yeah? That's why you may have big boiling from time to time. Because imagine you don't arc, so the bath is not moving so much. You inject a lot of oxygen because you are away from the target. And then you start with the electrodes to reheat the furnace, and then you get big boiling, all the slag and some still on the furnace platform. Why? Because you are away from the equilibrium here. Oxygen solubility is too, let's say, overpassed. Yeah? So you have to take care when you inject oxygen to do it carefully. Yeah? Same if at the later stage, because oxygen solubility is also related to temperature. If you have reached 1580, 1590, 1600 degrees C, and you still have a bundle of scrap hanging to the wall, which is falling down into the bath, then of course temperature is dropping immediately, and you force the oxygen to come back to the equilibrium very rapidly, so you get a reaction. Okay?
Excuse me?
Yeah.
Could you explain in more detail the relation of carbon and FeO? As you said before, as according to the carbon content is increased, the Fe content in slag is lower, right?
I didn't say so, but something like that, yeah.
Yeah. Yeah.
You mean that if you have here the carbon content of the bath,
Yeah.
and here FeO in the slag,
Yeah.
you have something like that. This is what you mean?
Yeah. Right.
Yeah.
Mm.
Yeah, this you can calculate by the thermodynamic.
Yeah. I'm sorry. You explained the CO bubble and the FeO interaction
Yeah.
like this.
Yes.
I think the carbon can react FeO and can remove O with the FeO, right?
With the reaction
Yeah.
FeO
Yeah. FeO plus C,
plus C.
Fe plus CO, right?
Yeah.
And when you denoted the FeO, will not change. The CO bubble, the
Yeah.
FeO, exactly.
Yeah.
I think the FeO
The question is
should
what?
change the Fe.
Yeah?
나중에
Yes.
슬랙 포면 할 때 나중에 일어납니다.
Yes, yes,
아,
yes.
네.
You create FE, you reduce the, I mean, of course,
Yeah.
you reduce the FEO content of the slide, and you have a lot of FE, you see it's blue, you have a lot of FE in the slide.
Yeah.
If you take a sample
Yeah.
with a spoon of the foaming slide,
Yeah.
first you find bubbles, yeah, and you can have down to only 3% of, let's say, material in the volume.
Yeah.
Yeah? That means you have 97% of gas and only 3% of condensed phase, yeah, for a good foam. But this is not the point. In this slide you take, you still have 15% iron metallic, 15 to 20% metallic iron. Yeah? Yeah.
But do operators can meet that percentage? Actually, when I see the specification from foreign suppliers, almost all suppliers mentioned more than 25 or something.
Ah, this is different.
Yes.
Here, you still have the, at the end, when the, okay. This is also something which is funny to me. You have the furnace here and the door. Huh? Here, the bath and the nice foaming slide going away. Eh? In this slide, you have here FEO plus FE.
Yes.
So when the people are specifying 25% FeO, they usually take the sample at the end of the heat. Yeah? Before tapping, they take sample of slag and they analyze it and they find 25%. Which is, let's say, not representative because the slag is starting to getting out much earlier.
Yes.
Okay? And secondly, so we will talk about that later. Secondly, when they take the sample, usually they are going to the lab and the lab is crushing the slag, removing the magnetic particles, and then they analyze what is remaining. So they are just ignoring the Fe, metallic Fe. So over time in the past, I was asking the lab to crush and to weight the non-magnetic and the magnetic to have an idea of how many iron, metallic iron is getting out of the furnace. Then what I say that taking the last sample is the lie. Because in conventional furnace, especially nowadays with the supersonic injectors, people are starting oxygen injection for the beginning. You have still scrap in the furnace, you don't have access to liquid pool, but they inject a lot of oxygen, so they burn iron. Yeah? Okay, you have a picture. Oh, I have to smile because I'm on the field. Okay.
Tomorrow you need cosmetic.
Yes, sure. I have to go to the hairdresser. Okay. So,
충분할 것 같은데.
let's imagine a furnace. Here you have the electrode, and here it's full of scrap, still full of scrap. Huh? On the side you have the oxygen injector. So you create here a huge pool of FEO. And at the beginning it's 100% FEO, yeah? And there is no access to inject carbon, even if, let's say, furnace supplier are saying, okay, this is a module, on top you have the burner, and then below you have the carbon injection. But most of the case, carbon is remaining here because there is no room and there is no liquid to react. And the FEO is escaping. So what's happened when the scrap is going down, yeah, and the first slag is going out of the furnace, yeah, and the first slag is going out of the furnace. In this primary slag, you have up to 60% FEO. And this slag is never analyzed by the people. So they think they have 25%, but in reality, they have in average maybe 40, maybe more. Who knows? That's why the corn steel and the COS have a yield advantage of about 1.5% compared to conventional furnace having a high oxygen injection practice. Why? Because the scrap is brought by the side. Okay, I will do again another one. Yeah, you have this is the furnace. Scrap is brought by the side here. So this area is free for the hot hill and liquid slag. That means if you start injecting oxygen and carbon, they can react in the slag. And the slag remains all the time from the heat with low FEO. Yeah. As in a conventional furnace, there is no access at the beginning for carbon injection. Even if you inject carbon by the door, the carbon is burnt on the surface and from the air ingress. Contribute surely to the thermal balance, but not to the air oxygen equilibrium and the down below. So that's why the early slag in the conventional furnace is high FEO, but as soon as the slag is accessible to the carbon injection, you can reduce the FEO of the slag by carbon injection, and at the end you have even less than 20% FEO in the slag. These are the goods. Okay.
좀 쉬다 하시죠.
그럴까?
네.
잠시 그러면 10분 take a break.
Okay. Cigarette break.